Okay, guys, this is the basics of how magnetism works and how we can use that to generate wind energy. So, let's start with a basic magnet here, right? If you split it right down the middle, you're gonna get south and north. And from there, you're going to get field lines that move from north to south. And they're going to wrap around like this. They're going to point in that direction. Same with the other way. You're going to get field lines that go like that. Oh. Type of thing. Right? And a way to see if two magnets are going to attract or repel, let's add more directional lines here. Right? So that's going that way. Just complete the loop like that. So if I bring another copy of this magnet close to here, right? Okay, I messed up the arrows in the last one, but now if I bring this magnet close, you can see over here that these field lines, when they interact, these two over here, I'll use different color, these ones, they are opposite, and these ones are also opposite. And what do we learn? Opposites attract. So these magnets are going to be attracted. That's why the north end of a magnet is attracted to the south end. And conversely, if we wanted to go the other way around, we could paste that in and flip it. Pretend that the text there is not flipped. And we bring the magnets close together. Here we go, sorry. We bring the magnets closer. Here we have like charges. Here we also have MS Paint fails, but here we have like charges. So both of these charges are down, which are like. Both of these charges are up, which are like. And like charges will repel. That's why you can't push together two north ends of a magnet, because these two field lines will repel. So that's one main thing you have to know about magnetism. All right. Another thing you should know is, let's say we have a wire. Let's make this our wire. And there is a current flowing through this wire that is going this way. It's going this way. Okay. What we can do is use what's called the right hand rule. So if you have your right hand, you stick your thumb in the direction of the current. If you see the directions that your fingers curl, that's actually going to be the direction of the magnetic field that's formed around the wire. That's right. Everywhere that there is a current, there will be what's called an induced magnetic field around the wire. And these induced currents are called eddy currents. So here, if you stick your thumb this way, you're going to see that your thumbs wrap around in that direction. So the eddy current is gonna look like that. And this is a field that is present all throughout the wire. So imagine this kind of cylinder of magnetism that follows this type of loop. Now, what happens if we were to put two of these together? So another useful notation to know is if you see a wire that looks like this, you can think of a wire as an arrow, right? So that's the head of the arrow, and those are the feathers, right? So you may see a wire like this or like this. Think of this as the end of the arrow, which means this is going into the page because the arrow is being shot into the page, let's say. And this to be the tip of the arrow because this is being shot out of the page. So using the right-hand rule, we can determine that the eddy currents of a wire coming out of the page are going to go in this direction. Or counterclockwise. And going into the page, conversely, will be clockwise. So now we're going to move into why conductors work. So inductors, in case you are unaware, are when you have some form of cylinder here. Let's say it's a hollow cylinder, not a ferromagnetic core. And you take a wire and you wrap it around the cylinder many times, and a few interesting properties come up. And let's say you connect these between a battery, and then a current begins to flow that way. A few interesting properties come up, so let's take a look. So when you do have these inductors, or solenoids, if you will, you could take a look at a group of these cables, right? And these are all facing the same direction. So let's call it going into the page. So this is coming out of the page, and the subsequent magnetic field will be counterclockwise, like so. Just check that with the right-hand rule for sure. So we can copy this, make some sort of an array of these wires here. And what you may or may not notice And something I failed to mention earlier with bar magnets is uh, if you cut a bar magnet in half, and you could easily put a point of inquiry here, say, you know, what might happen if you cut a bar magnet in half? Could be a fun question. Right here. Like that. Is south red? Or is north red? Which one's red? Whatever. I'll check. Okay, yeah, south is blue. So let's call that north. Call that south. Okay. So if you cut this bar magnet in half, let's make it black. If we cut this into two smaller bar magnets of, let's say equal size, not equal size, let's say equal size, then what do you think will happen? I feel like, you know, presenting this to kids, they might say, oh, the south side will stay here, and the north side will stay here. Interestingly enough, ferromagnetism is a materialistic property, so these will actually remain split. So once you split them, they will split up a magnetic field within themselves, and it will go in the same direction as it did before, north and south. And this is another cool thing right here. If we have these two adjacent bar magnets, what's actually going to happen, because they're attracted to each other eventually, this north is actually going to, this north is actually going to go to this south in both ways. And then this north is going to wrap all the way back to this south, like so. And if this was sliced and placed back together just like this, because of how this field of magnetism works, it would in effect work as if this was just one bar magnet. Because when these field lines on a bar magnet go from north to south, they don't actually end. They continue sort of invisibly throughout this bar magnet and go in that direction. So you can, when you put it like that, you can quite visibly see the parallel between cutting a magnet in half and just placing those two magnets close to each other, and a magnet like this. And similarly with these magnets, there is an invisible sort of continuation of the field here. Obviously, you know, for modeling purposes, we'll say it's a field. In reality, there's the entirety of magnetism is just fueled by special relativity, but we're not going to delve into that. We're instead just going to go back to our example of an inductor here. So here we see some like charges. Wonderful. We love to, some opposite charges. Wonderful. We love to see opposite charges. That means they're gonna attract. So they're gonna attract in a similar way to this attraction, in the sense that you can basically just treat it as one continuous field, like so, presuming these were equidistant and of equal current, which they are if they're wrapped in a coil. And this this like charge thing can obviously expand to the entirety of this of this inductor, no matter how many times you wrap around, which is quite a lot of times actually in the motors we'll be looking at. Then you'll kind of have this continuous magnetic field. But you have to remember these are wires that are coming out of the page. So we've actually kind of rotated this to look at the magnetic fields here. So actually what we're looking at coming out of the page is a set of probably over there would be a good way to put this. So we've sort of drawn out this. I'll try to make it go behind these. We've sort of drawn out this magnetic field that goes behind these guys. And if the current's going that way, yep, coming out of the page, then this will go like that, and this will go like that, this will go like that, and this will go, sorry, this will go like that, and this will go like that. And that wraps around the whole thing. So now we have a whole, from magnetic fields going in one direction, we've sort of grouped them to have all these fields going like that. And if we label the current here, it might be much easier to follow. So the current is going to go like that, like that, like that. It's going to wrap around and go like that, like that, like that. So that is the arrowhead basically coming out of the page, right? And it's because of this that solenoids end up forming these really neat magnetic fields where if you have a solenoid, I'm actually just going to paste in a drawing here because I'd be pretty useless at drawing this. There you go. Because if we have this solenoid now, I guess if I rotate it, it might be easier to see. That, yeah, we do have that magnetic field carrying over like that. And it also causes these, obviously every field here is a collection of a bunch of fields that goes around and around, basically forever, and also internally forever. So this is a better representation, I suppose, of that loop. So these obviously go around and complete a loop like this, and so on and so forth. And yeah, so these are what the magnetic field lines look like around a solenoid. So even though you're putting current in this direction, you actually get a magnetic field that goes out like that. And what this does in effect is turn it into a bar magnet, because what else do you see with field lines like that? If you put this horizontally and drew those same field lines coming out there, going in there, out there, in there, well, we just have a bar magnet, right? So going out there, that's going to be our north. Coming in there is going to be our south. And these field lines have this sort of invisible, I guess it's more visible in this diagram of a solenoid. But this way you can turn current through a wire into a bar magnet, which is pretty neat. Now, you very well may be asking, or screaming at your monitor in fact, Zane, what does this have to do with wind turbines? That is a very valid question. Allow me to put your mind at ease. So, in the same way that current can be transformed into a magnetic field with solenoids, That B is the sign for magnetic field, by the way. Magnetic fields can be transformed into current using a solenoid. Isn't that funny how everything balances out like that? But without getting too existential, let's set up a solenoid for ourselves. So if I draw... Oh, this is an awful drawing. Let's draw a solenoid like that, right? And let's pretend that it doesn't look like a toddler who drew that. Current flowing this way, that means it's going to be up this way, it's hard to follow, up this way, up this way, and go down, right? I wanted to just make it a little bit 3D here. That's why it looks weird and skewed. But we're going to go back to our old friend, the bar magnet. Alright, we're going to bring him in here. Let's make ourselves a good old bar magnet, right? So, oh, I want that. I just want it to be black. Okay, whatever. There, then that, then that, then that, then that, then that, then that. Than that. Oh, and I should mention with solenoids, there is a third right-hand rule that you can use. So if you wrap your fingers in the direction that this current is going, so basically, you know, your index finger should be pointing up and then curling down, and your middle finger should be pointing up and curling down, and so on. Then you stick out your thumb, which should be pointing to the left right now, is actually going to be the direction of north in this induced magnetic field. So we basically we can put a little north here and a little south. And if you really want, we can draw out our magnetic field lines like that. That's not dotted, actually, in the middle. I don't know why I did that. There, 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 and there. Right? Let's just finish up our bar magnet here. Again, these all have many, many more layers of magnetic field lines, but for the sake of simplicity and time, we're not going to do that. If I select this whole bar magnet here, oh shoot, it's going to do that. Okay. And let's say I hate that it's can I bring this under? Perhaps? I don't think I can. Okay. Nevertheless, if I bring this into here, it would be more appropriate if these signs were flipped, actually, because these charges would repel, these internal charges, this whole thing would just explode, right? I don't think this can exist in the real world. If we flip this horizontally, now we're fine, right? Except for these two letters being wonky. This north is attracted to this south, this north is attracted to this south. This magnet just wants to sit in the middle of that solenoid and not move for the rest of eternity, right? Things in the universe are inherently lazy. They don't want to move. We call that property of laziness inertia. So when something comes along, let's say my finger, and pushes that magnet out of the way, then there's actually going to be an opposing force created to keep this magnet where it was. So there's gonna basically be an effort made by the magnet to make a stronger magnetic field in this direction to push it back. And actually, in real life, it would kind of wiggle wobble until it got secured back into that place. Now, this induced magnetic field caused by the induced current, also known as EMF or back EMF, will happen regardless of whether or not there's already a current in the wire or not, because of this changing magnetic field. When I put this magnet in here initially, and let's say there's no current flowing through this solenoid already, the fact that there's a magnetic field going through these wires, where you can kind of see that it wants to have created that that structure that we had before, where it was sort of a long thing like this, an oval type of shape, and this would be coming out of the page, right? Where you can see that it sort of wants to make those magnetic fields, it will induce the current to kind of make that happen. And this relationship, this is called Lenz's law, and Lenz's law is a relationship defined by this, technically, if you want to get fancy with it. It's like this, which just means this is basically just describing this just means like a three-dimensional change in magnetic flux over change in time. So basically, how fast is the magnetic field changing in each direction will define how much induced EMF or induced current will happen in each direction. EMF is an electromotive force, and it's funny, the word motor is used, and N here is the number of turns in the solenoid. So you can really see that these are all linked together. You know, this is the moving magnetic field, this is just the speed at which it moves, this is induced, well, it's induced voltage, but that leads to the induced current, and this is all very cool stuff. So basically, if you move a magnet near a wire, there is actually a small amount of current that's produced, and if you wrap those wires really tightly into what almost it sounds weird, it's almost what wants to be a magnet, it's going to create a magnetic field there, and then it'll be at rest. And then if you change, it's always proportional to this change, right? This is a derivative, so you're looking at change. It's always proportional to that change in magnetic field and how quickly you're changing it. So if you super quickly shake that magnet with your hand, let's say, like that, then it's going to induce a lot of current. And this is the foundation on which wind turbines, or hand cranks, or really motors, any sort of thing that's transferring either movement to electrical energy or electrical energy to movement. This is the basis. This is the foundational. This is the foundational logic on which those methods, those inventions are built. One of which is the wind turbine. So, let's say we have a coil like this. You wouldn't build it like this, but let's say you did. And like this. And like this. And let's say you had a bar magnet right here, with this being north, this being south, and I'm going to try to keep this compact because this is going to be spinning. But obviously, keep in mind these magnetic fields are way bigger than I'm drawing them out to be. So, is there a rotate tool? Can I rotate? I can't spin it. I can only rotate it. Okay. that I'll have to do, I guess. And you can see, basically, the idea is when it's in this state, it's at rest, right? The change in magnetic flux over time is going to be 0, no matter what. If I rotate this, then over the course from there to there, this magnetic field, it hasn't changed in strength, but it has changed in direction. And magnetic field is a vector. So a change in direction will cause some acceleration in the derivative of that vector. So that will, that rotation will induce current in all of these fields, because the magnetic flux will change, because if this is oriented right, it will change the same amount in each of these inductors, and it will induce the same EMF in all of those inductors, and that will produce a current. That current can then all just be put into some form of central battery storage circuit, something. But this is basically how you generate electricity from a magnet, from a wind turbine. You're having this, let's even if this is a hand crank, right? Let's say you're manually turning this magnet. If you manually turn this magnet in the middle, and you have these inductors along the sides, then this changing magnetic field will cause a current in these inductors, and that current will go to fuel a battery, a light, I don't know, whatever. And instead of, manually hand cranking that magnet is being turned by turbines, which are, bent and set up to have the wind rotated in a certain way at a certain speed under certain conditions. And actually, this is not just a bar magnet laying like that, because there's 3 inductors. There's actually also, and it can be more than 3 inductors, but in a simplest case, it will be 3 inductors. The reason you can't have 2 is because it's something called gimbal lock. It could just get stuck like north to south here and south, like north to south here and south to north, if there was just an inductor here and an inductor here. But because there's 3, it'll never get stuck. 3 or more, it could work. It might get stuck with 4 as well, right? You can have some gimbal lock, but less. Either way, this is also not technically the final model. It looks more like there are some curved kind of magnets, and they're split like this. And this way there really can never be any gimbal lock, especially if there's an even amount of these. Then you get, like, let's say a north, and a north, and a south, and a south, and a south. And this is just kept in some form of core. Normally what we call a ferromagnetic core, which is just some type of iron core that can help induce electricity. Same with these inductors. They have a ferromagnetic core inside of them generally. So that's a term you might want to know. And then there would be these coils, this coil, and this coil. And this would just be, spinning around, changing the magnetic field up and down and sideways, and that change in magnetic field will cause an induced current in these coils, and that induced current will come all the way to charge a battery, let's say. In the simplest case, it'll just charge a battery. And that, ladies and gentlemen, is how wind turbines work with magnetism. Let me just make a final little thing here. Yeah, that's basically all you need to know. Those 4 little mini lessons break it up. That's how wind turbines work. Congratulations. You can now go out and make, I thought I wasn't recording for a second, I had a heart attack. Now you can now go out and make your own wind turbines. Congratulations.